Let A be an n by n matrix with the entries little a sub ij. The determinant of the matrix A is the scalar here. Now remember from the intro video to this lesson that the determinants over here and so on are called the minors of the matrix A. So in particular, capital A sub 1, 2 and capital A sub 1, 1 and so on, whenever we're talking about determinants, they refer to the matrix I defined in the previous video, in the intro video for this lesson, and not to the ij entry. I want you to notice in particular that the definition of determinant is recursive. So in order to define what the determinant is of a 4 by 4 matrix, you need to know what the determinant of a 3 by 3 matrix is. And in order to define what the determinant of a 3 by 3 matrix is, you need to know what the determinant of a 2 by 2 matrix is. And there we can stop because we know what the determinant of a 2 by 2 matrix is because we've already defined that explicitly. So let's look at an example. We're going to compute the determinant of this matrix A. The determinant of A is equal to the following. So we first look at this entry here, that's little a 1, 1, and we then remove the row containing that entry and the column containing that entry, and we take the determinant of the matrix that's left. So this is 2 times the determinant of the matrix 1, 0, 0, 0, 2, 3, 0, 4, 5. Then we do minus the same thing for the next entry, but that entry is 0. So we don't even need to go and figure out what the minor is for that entry. We just put a 0 here. Then we do plus, and now we have a 1 here, and we remove the row containing the 1 and the column containing the 1, and we take 1 times the determinant of the matrix that's left over. So that's the matrix 3, 1, 0, 1, 0, 3, 2, 0, 5. Then we subtract what we get for this entry, but again, that entry is 0, so it doesn't matter what the minor is, we just put a 0 there. Now we can go continue computing. Here we have 2 times the quantity. We have 1 times what's left over when we remove that row and that column. So we get 1 times the determinant of 2, 3, 4, 5. But the rest of that row is 0, so we have minus 0 plus 0. We still have this minus 0, then plus 1 times the quantity 3 times the determinant of 0, 3, 0, 5, minus 1 times the determinant of 1, 3, 2, 5, plus 0. We know how to compute these 2 by 2 determinants from what we've learned in a previous lesson. This is 2 times, let's see, 10 minus 12 plus 3 times, 0, minus 1 times 5 minus 6, which is going to be negative 4 plus 1, which is negative 3. Something that made this computation not take too long was that this matrix had a bunch of zeros in it. If there aren't very many zeros, computations using this method can be very long. Luckily, There's some better methods, which we'll learn about in the next two videos. To simplify notation even further, so to simplify notation even further, we define C sub ij to be minus 1 to the I plus j times the determinant of aij. And we call this the ij cofactor of A. Do not ask me why it is called a cofactor, because I do not know. When we use this notation, the formula for the determinant is then the sum from j equals 1 to n of a1j, that's little a1j, times big C 1j. In honor of the name cofactor, because people, I guess, liked it so much, they thought they were super clever for naming it cofactor and being very not obvious what it means. We call this a special name. We call this the cofactor expansion along the first row of A. Now notice that I said first along the first row. Well, it turns out that any row works. In fact, any column works also. Which brings us to the following video. You thought I was going to say theorem, didn't you?